Our next session is entitled The Role of Technology in the Future. We have two guest speakers for this session, and again a panel will join them on stage and go in depth into the topic after. I would like to introduce you first to Dr. Geza Kogler. He's currently the Director of Master of Science Prosthetics and Orthotics program at Georgia Institute of Technology and Principal Investigator for the Clinical Biomechanics Laboratory. He received his baccalaureate degree from Wayne State University, Detroit, Michigan in 1982, a postgraduate certificate in orthotics from Northwestern University Prosthetics and Orthotics Center, Chicago, Illinois in 83, and his PhD degree in bioengineering from the University of Strathclyde, Scotland in 1998. So without further ado,
thank you, David, for that introduction. Thank you for the organizing committee to invite me to this beautiful city. It was really difficult to get me here. So, this title, Brace Yourself, It's Coming, I think you all know that it's already here. What I'd like to do is just give you some perspectives as an educator, clinician, and scientist. So we've already heard this a number of times this morning, wearable technology, and that is the domain we live in. And I'm just wondering what this guy's looking at in those glasses, and I hope he can see a little bit beyond and where we're going. But in my interpretation, that this wearable technology, at least the way it's perceived, is code name for cool stuff for orthotists. And at least that's what the students tell me that I work with that are intrigued. Thing is that we've got a long history of this. This is a picture of actually in one of our early atlases from the early 50s. And so we've been doing this an awful long time. Here's another version of it, actually built out, which is on display at the Science Museum in London. We actually have some expertise with wearable technology. And so this is not unique to us, except for the way that it's being perceived. So what I'd like to talk today about is the technological advancements that I think are going to lead to some major changes in orthotics. And as a clinician first, with 25 years of experience, always in academics, and then later being able to build out a lab, I've had the privilege of being able to answer questions that I had as a clinician. And that's really how I ended up doing these areas that I will discuss today. So instead of a crystal ball of like what's going to happen and where we're going, I'm going to present to you the areas that I'm pursuing research-wise and the ways that I'm approaching our educational program. So this is actually realistic. So I developed a clinical biomechanics lab shortly after joining Georgia Tech about 8 years ago, and this is my lab. And the lab is really about students, because students are the ones that make this lab up. And this brings me to the connections to this technology is really based on education. It really is the key mechanism so that we can integrate with this technology. And if you look at our MSPO program at Georgia Tech, we were the first, so we had, we've been around for about 14 years. We also have another first, is the first PhD program with an emphasis on P&O research to train scientists to do this research. We've graduated about 120 graduates with a master's degree, and the total now coming from the States is somewhere around 430, 440 with the other schools that have gone to the graduate program. In just a little over a decade, we've been able to influence the individuals coming into the profession. And it's these new individuals that have come into the profession that are allowing us to engage. So this is a mantra, at least at Georgia Tech, the way that we've been established. Our program is a little unique in that there's a strong emphasis of science, and we have capstone research projects. And on our outstanding capstone research prize that's given out annually, this is on there. The Master's of Science program in Prosthetics Orthotics emphasizes translational research and its clinical relevance on optimizing patient care and the role science has in ensuing positive treatment outcomes and best practices. Because most of these students want to be clinicians, and they're like, well, why do we have to do all this research stuff? And this is the reason. So we're trying to set the foundations really early on for these students. And one way we have to keep these students interested, one way is keeping them engaged. So we just recently, only a year ago, formed what we call POTUS, Prosthetic Orthotic Technology Innovation Studio. And this is just a lab with a lot of computers and 3D printers. And it's designed to encourage the students to engage technology. Now, our lab is not equipped with any P&O type equipment. We don't have a suite of warm equipment at all. But our students are using this equipment in a different way. We're training them to be with enough engineering that they can use the latest software packages, like SolidWorks. It's an engineering software package to model things. And we're having them design parts for devices, designing the research apparatus that they'll be using. So in order to keep these students interested in, this is one way we do it. These are a few of the lines of research in our lab. One is this wireless instrumented AFO, which I'm going to talk about. One is looking at foot tissue stiffnesses, which I'll introduce. Portable powered assist ankle foot orthoses. And there's a powered sit-to-stand device that we're also making. All these are funded by U.S. extramural grant funding, National Science Foundation, NIH, DOD. The money's there. They want to fund these projects. So some of the reasons why these were pursued, primarily because you go where the money is. So what has this graduate education done? It's given us new interdisciplinary skills. So before, when the entry level was at the bachelor's level, we had students that had a bachelor's degree in P&L. What's been really great, those 400 students that are out there have additional skill sets, like mechanical engineering, biomedical engineering, bioengineering. That has enriched us, and that is why we've got people that actually know about this technology and have these skill sets to interact with it, working on our teams to do this. Now, those areas that I showed you that are working on in my lab is all being done by students who have only just an exposure to clinical practice and are now making a difference. So I'm going to cover 3 broad topics, and I'm going to present it in ways to show you some scenarios that connect clinically. Sensing, power, and CAD/CAM. What we need is the ability to measure stuff, and we don't. We've been measuring for years. We measure how to fit a device and take measurements of a patient and get those to match. But we need measurements relate to what we do. And so this is the most important part. How do we get there? Well, we have some great models. Medicine has tons of models that we need to follow. So if you look at cardiology, they have all sorts of clinical diagnostic tools. If you look at resting heart rate, blood pressure, total cholesterol, those are ubiquitous in a society right now. We all know what those are. Your cardiologist, if he walks in, won't even touch you. In fact, goes a step further. He has all these additional clinical tools to take measurements before he even starts to make a clinical decision. What we need is a list like that for orthotics and prosthetics. And that's hopefully where we will have to end up there, because it's needed and it's the way science gets integrated into medicine. So what will that look like for us? So we're going to talk about sensing, and by sensing I'm talking about measurement. That's all I'm after. And there's a lot of things that can kind of help us out. Here's an example. So we have an AFO and we have a limb, and I focused this presentation basically on lower limb. This can be transferred to many of the other areas that we work in. But these are things that I think are important to us, that our devices that we provide relate to. So understanding what an EMG response is to when the user is using a device, an AFO, the interface pressures. We are applying forces to an extremity, it would be helpful to know what our interface pressures are. What's the ankle torque that's generated by the AFO that we fit? Who measures that? Heel contact and forefoot contact sensors, that's just no more than a pressure sensor that can sense. And that can be used to determine what the gait states are so that we can evaluate our subjects wearing this instrumented AFO. And what we're looking at is, as orthotists, what we do is we control motion. We're motion people. We actually have to control motion. So let's measure it. Let's measure what movements are occurring at the foot, at the tibia, and what movements are controlled in the ankle. This is what it will look like for us. So we began looking at developing different instrumented AFOs. These were all done as capstone projects for students. And we're in about our 4th iteration now of the designs of these. Each one had a different target concept that they were trying to pursue. And all these projects actually led to us getting our first grant. So here's one, and you can see that there's a load cell that's attached to a spring. So that our spring is basically the AFO control mechanism, that we could change out any type of stiffness we want. Then we had a little potentiometer at the ankle to measure ankle movement. We have force sensors in the shoe. We had, this particular system was wireless, so we had Bluetooth technology, and we could collect that data on a tablet. This was done by an MSPO student as a capstone. What are the uses of something like an IFO that can take all these measurements? Well, it can be used as a diagnostic measurement tool, just like the cardiologist. First thing, before you even talk about what you're going to do, you put this device on, you take a series of measurements. It has some algorithms to tell you how you might target a prescription, and you're off to go. It can be used for performance measurements, and it can be used to monitor a user's progress. This is not an everyday user device. This is a tool to take a series of measurements to help you with your clinical decision making. This setup is its own gait lab. Here's a overground walking. This is being done wirelessly, and the individual's walking, and this is the data output on a tablet that can be done. I didn't put it up here, but that ankle angle as an example is showing you in the gait cycle, and each one of those colored zones is a different spring stiffness that's occurring. And then there's the ankle torque that is generated by the different springs. A lot more data that it produces, but the idea is that I now can look exactly what stiffness I want to hone in on for that patient to optimize this individual's walking. Now, there's a little bit of a departure here real quick. Most of the AFOs we fit are designed for that task. And the way that we measure it's quite crudely. We often, a clinician will put an AFO on a table, put their hand on the foot plate, and then they'll check the stiffness by the hand, and that'll go. If we can see the toe clear the ground, we're happy. The problem is that they actually are on the ground more than they are in swing phase. And we perturb them by that stiffness. And those stiffnesses vary. So, sloped walking. Our muscles are used differently to manage sloped walking. Some of the hardest challenges we have. So there's different stiffness parameters for that particular task. We can measure it now with this tool. We can also measure going up and down stairs. I don't need a gait lab. This is what I view as a very good diagnostic tool. Here's the first version that we had to show you its simplicity. So we have a load cell that has connected to a series of bungee cords. We had to calculate torque using that particular system, and then we have a little encoder to measure the ankle movement, and of course our force sensing resistors. Again, another capstone project, and this is the data. So I think we all know that when we put an AFO on with a given stiffness, that we recognize we're probably influencing the amount of dorsiflexion and plantar flexion during stance. I think we all know that. But how many of you actually know how much? So here's an example of what data we got from that IFO. If you look to the left, that blue line shows 15 degrees of dorsiflexion range of movement when the AFO has no bungee cords on it. As expected, with increasing bungee cords, increased ankle torque, there's a decrease in ankle range of movement. We're now perturbing that individual's walking. So we may achieve swing face clearance, but not optimally. So this puts it into a little bit better perspective in terms of percentage. So you can see with like 2 bungee cords, 19% reduction, 22. I think we have up there maybe 43%. 43% reduction in range of movement at the ankle, that relates to step length. That relates to speed of walking. These are outcome. These are performance measures, but it relates to outcome measures. So things we learned from the IFO, this can be learned in the clinic with these types of measurements. Undue AFO rigidity. I've always felt that we've been over-engineering AFOs. So like one take-home is that for every 1.75 Newton meters of torque, there was a 1 degree loss. Say, oh, that's no big deal, but that's 19% of range of movement. That's just one example. So it gives you an idea of how that can be useful. This is something really simple. So we're making an AFO that's designed to apply a force, and most of us don't take a measurement of how much load, how much force it takes to lift the foot to neutral. Well, here it is. It's about 2.5 Newton meters that it takes to hold the foot up to neutral. So that should be the target stiffness for at least target stiffness for how you're going to design that AFO. Well, that falls right here on that scale of where that is. So there's a loss. So everything that's stiffer than that is a problem. And we still have a loss of range to have it that stiff. So it gives you a perspective that this is here, this is what we're measuring, and we've got some advanced iterations right now of this IFO that will actually change the way we design AFOs, in the sense that now I have the stiffness parameter that my IFO can tell me exactly what the stiffness should be in both plantar flexion and dorsiflexion, and they're different, but the AFO doesn't exist now, because we don't even know the stiffnesses of the AFOs right now. Manufacturers aren't telling us, hey, this has a certain stiffness in dorsiflexion and plantar flexion. So the next generation of AFOs that will match this will have to look probably different. So let's talk about power. I think some of you have seen some presentations or read in the literature about powered exoskeletal systems, and it seems so distant, and why would we even want to go there? I hope to reveal a little bit that. So we're just talking about adding a motor to a device. So what the limitations, as you know, is all our devices are passive, and so we can't get active plantar flexion, which is important for mobility. And so there are some advantages of looking at power, and there's options now with advanced electronics, pneumatics, hydraulics, that there's possibility of doing micro versions of that could be useful in clinical practice. So we've done I've been involved in some development of some powered orthotic systems. And as the only medical consultant on the project, I was able to steer things to look at clinically, which was helpful. So, and that was coming up with some metrics. So we came up with metrics of design before we designed the device. Things like how much power would be applied to the load, a goal of how much power, 10 watts for an AFO, to less than 100 watts, metrics of size and weight that are approach less than 1 kilogram, similar to what a conventional AFO would be. And then a lot of these powered systems are tethered, which is not practical in a clinical environment either. So could we make one untethered? And then could we have that device work for about an hour, as an example? So with some of those target measures, this is what we came up with. So now I'll mention that this is all proof of concept. So we took off-the-shelf parts that met all those metrics and came up with this. And I'll explain what those parts are. So it somewhat simplifies what we do. So using the same techniques for the instrumented AFO, we had pressure sensors so we could determine where gait states were. We had sensors on a motor to determine what the angle was. And then we have an onboard computer or microcontroller that control valves. that can regulate and control an actuator, and it's controlled with a small compressed air gas tank. And so this is what that system looks like assembled. So where we ended up is we met our metric 1. We had adequate power. We did not meet our metric 2. Ours was much higher in weight than we thought, but as a design constraint, we knew that we probably wouldn't meet that metric. And we were able to make it untethered. So this is the first untethered powered AFO that we're aware of. So from this experience, we learned some things, and that was that for efficient and effective delivery of power assist, the extremity, that is important for the performance. But it was based on the neuromotor response to do that. So we can learn some things, and I'm going to explain that. So the way the body works is we have an internal motor function that makes those movements. So it basically is a system of pulls. So we pull for dorsiflexion, we pull for plantar flexion through that retinaculum at the ankle. But the way that our AFOs and these powered systems work are they don't work the same way. And that's a bit of a problem because we're asking the foot to go through a movement that's applied with an external skeletal system. Or we want to hold something and it's done in an opposing way. So if we look here we are pushing to hold the foot in dorsiflexion. We're pushing from the bottom of the foot, we're pushing at the calf band, and we have a strap. Totally opposed on the way the foot and ankle try to move together. And so that creates a different response mechanism. Now that's really important because I think that's the unknown domain that has the greatest potential for us to expand what we do. And that is, we need to have a better understanding of what the human response is to exoskeletal orthotic systems. How does the body respond to constraint of movement, which is what an AFO does? It responds in different ways, and we're just learning about what those are. So taking this tool, this powered AFO, we did a series of experiments. It was a 15-minute walk on a treadmill. And if you look, the orange zones are the zones where the power was off. And in the middle there is where the power was on. What powered on mean is that the scientist or the researcher could hit where the power perturbed the movement in the middle of the movement, either in dorsiflexion or plantar flexion. So what does that mean? So here's a slide that shows the results of the after effects. And I'll just look at, we just look at pre-swing, for example. So the blue areas are where there's no power. They're just wearing that powered AFO walking. And so when they turned the power on, it started to change things. So white is plantar flexion power, black is dorsiflexion power. And if you look, when they started to power it on in that orange zone, it still persisted after. Now, why is that important to us? Because that's possibly a new treatment paradigm where that could be of therapeutic benefit. That for a period of time I'm powering, and the power was off at the end there, but you still had this after effect of a response. And we believe that these types of things can actually be new ways in which an orthosis can actually be a therapeutic mechanism. Now, this wouldn't be something worn every day. This would be in a therapeutic setting. Now, we don't know how long that after effect would last. Chances are it may die out, but it may actually stimulate rehabilitation of that individual for greater mobility in those areas. So again, I think that this is an opportunity for this to increase our practice domain, and there's quite a bit of funding right now, at least in the US, in looking at neuromotor response to constraint of movement or blocked movement. Okay, CAD-CAM. So there's quite a bit happening with buzz right now with CAD-CAM, and I'm a little bit concerned and I'm cautious with some aspects of it, specifically scanning. So here's a picture of a sculpture of a foot. I think you all recognize it as a foot, but it's stone. Here's a scan And that scan just gives an image of the foot exteriorly. And this is where the problem lies. It's hollow inside. And that concerns me. Because what I see happening is this technique for scan, print, and dispense. And for manufacturing, that has great value. But if we don't get, I think there's one more. I think if we can't, we have to get past the scan part, because that's actually the treatment part, at least in part. And so here's what the challenge is that we have as an orthotist. We have a orthosis that has to interact with the skeletal structure. That's a difficult task, because over that skeleton is all that soft tissue. And then and we control that by the geometry of the orthosis and then by the material, whatever that material is. And they have to mate. Well, between that orthosis, there's a lot of stuff. If you go from right to left, there's the skeletal structure, and you have all these tensile structures going across the foot. And again, what we see as clinicians is we're just looking at, a skin and that external surface. So this relates to another problem I have, is the fact that most of the foot orthoses are made out of one material that's isotropic. It has the same material property. But we speculate and have a good idea that maybe we should look at something where the properties vary throughout. Because on the foot, it varies, the different tissues on the foot. Here's an example of the same person, full weight bearing, with their arch, and that red line is the apex of the arch, partial weight bearing, and maximum arch height. 3 different shapes. But each one of those shapes, from maximum arch height, nowhere to full weight bearing, that's the treatment zone. And we've got to decide what that treatment zone is right there. So here's a tool that we developed in the lab, which is a different type of scanner. And what it is, well, if you want to call it a scanner, if you look at this slide on the right, that's a probe that has a load cell on it. It has a load cell on it, and can it measure the distance of compression of soft tissue at an exact amount. And that's the difference between an external scan of the foot, is that I now have engaged the soft tissue and understand how its densities and how it may perform, and actually give me a distance of measure of how, I guess I'm cut off. So the difference is that I believe that this is an approach to develop what that shape is, because essentially that scan you're taking is trying to get a starting shape. But unless you understand what the tissue is or have some control of that, you're not able to create that arch that you want. So what we've done is we've mapped the foot, and this is showing the different densities. And notice that and this is not surprising, that under load, because this is done weight bearing, those blue areas are the densest areas, and with the least travel. But in the arch, you see the greatest travel. So how can this help us? Well, if I took a scan like this of the foot and had measurements of the entire foot, I would be able to predict exactly the height of a particular element of that device. In this case, if you take metatarsalgia, and I'm going to create a metatarsal support, by such a technique, and here's the measurements I would take on the left, I can target exactly how much load it's going to take to displace the foot, and then target my metatarsal support height by doing that. That to me seems like a direct clinical correlation of how I would want to use a scan or a shaped starting point. So that brings us to a transition and integration of this new technology. And it really is, in part, a new set of skills and an expanded knowledge base. And our students are there at this level, because these students are already coming in with computer engineering degrees, electrical engineering degrees, mechanical engineering degrees, combined with a new degree as a master's student, and we're there. So it's all about the people. This is just, many of these students, they were all on different projects that directly relate to what I had shown you. Thank you.
Next, I'd like to introduce Matt Ratto. He's an associate professor, Faculty of Information at the University of Toronto, and directs the Semaphore Research Cluster on Inclusive Design, Mobile and Pervasive Computing, and as part of Semaphore, the Critical Making Lab. A current project involves the development of a cost-effective software and hardware tool chain for the scanning, design, and 3D printing of lower limb prostheses for use in the developing world. This work is being carried out in partnership with nonprofits CBM Canada, CORSU Hospital in Uganda, Autodesk Inc., and Toronto Prosthetics and Orthotics experts. Ratto is also Chief Science Officer at NIA Technologies, a nonprofit startup founded to deploy and scale his research on 3D prosthetics. Matt?
Although I was asked to speak kind of generally about technology and the P&O profession, I'm going to constrain my remarks really to digital fabrication technologies. I want to start, in fact, by doing two different disclosures. So one disclosure you already know, I'm an associate professor at University of Toronto. I'm also the chief scientist for NIA Technologies, which is this nonprofit. But I have a more important disclosure, which is I'm not a certified prosthetist or orthotist. And I have another disclosure. I'm not even an engineer, a bio, or any type. I'm actually a social theorist of technology who has found himself, strangely enough, in the role of not just studying the social implications of emerging technologies, but actually taking an active role in their development. And my comments today really start from that position, which is I'm really interested in the relationship between the social and the technological, and recently that's brought me to prosthetics. So that's where I'm starting from. And although I've been asked to talk about the present to some degree in the future, I actually want to do that by taking a step back. And part of that actually is in order to explain this image, which I'll come to later in my presentation, this diagnosis by radio from Radio Electronics magazine in 1925. So then and now, I want to talk a little bit about digital fabrication, CAD/CAM technologies. I'm going to do that by talking about shape capture, design and rectification, and fabrication kind of then, and take a look at it now in order to kind of make a point, a little bit of a point about these technologies. Shape capture back then, so these are a series of articles from the mid to late 1980s, early 1990s. We have Saunders, Fort, Bannon, et cetera, computer-aided design of prosthetic sockets for below-knee amputees from 1985. They used measurement combined with CAD software to produce prosthetic sockets for transtibial. We have computer-designed prosthetic socket from analysis of computed tomography data from CT data from 1989. We have a CAD/CAM method for custom below-knee sockets that uses laser scanning from 1992. And this is only some of the articles. If you go back and look back for this time period, you find really a plethora, a lot of research going on in the CAD/CAM area around the development, specifically of prosthetics, mostly focusing on transtibial, I think for some of the same reasons that I've worked in that space, which is at least to a beginner, it seems easier. Design and rectification back then, there was software of many different types. This is the only screen image I could find of one. This is a tool developed at the Rehabilitation Engineering Laboratory at the University of Texas. When I first started doing this work, I found this image and was struck by how similar some of the images, particularly these rectified positives there on the lower right, how similar those images looked to the software that I was actually working on as well, despite the fact that these were being powered by early IBM personal computers on vector graphic screens. Fabrication back then, this was an early version of a CNC mill, computer-controlled numeric mill, specifically developed for computer-controlled carving of prosthetic devices, carving stump models. This is from 1985. There's examples of this that predate this as well, dating back to as early as 1983. And here's the kicker. So if you go back, and this is an article by John Michael. I wish he was here. Is he here by any chance? I don't know if he's still with us. Anybody know this guy? Yeah, okay. So this is a fascinating article from 1989 when I came across it. This initial statement from 89, computerization will come to P&O whether we want it or not. That's not the surprising bit. This is the surprising bit. Current technologies provide mediocre results. Current technologies reduce the complexity of design and disregard crucial data. We are enamored of computerization and we imagine benefits that don't exist. This isn't the kicker. This is the kicker. We should embrace, encourage, and adapt computer-aided approaches to prosthetics and orthotics starting immediately. And this idea that the technology isn't there, that it's ill-suited for the job, that we're making broad claims about its appropriateness and its usefulness, and yet we should still adopt it. This seemed actually very much like what I was seeing in 2013 when I first started doing work in this area. And I was really struck by this statement and some of the reasoning that John Michael had around computer-aided design and manufacturing and prosthetics, particularly given the changes that we've seen between that time period and now. So if we look now at things like shape capture, we have a number of almost commodity technologies being used for shape capture, primarily involving structured light or lasers, non-contact forms of scanning, ranging from things like the body scanner. By the way, these are taken straight from TechMed's website, so Benoit, if you're here in the room, thank you. Hope you don't mind me stealing stuff off your website. But it's an interesting correlation here between a $15,000 and $400 scanner that are now on the market. But this is where we're now at in scanning. Anybody can go and buy these scanners. Design and rectification, there's a range of opportunities ranging from Vorum's CanFit software to biosculptures, I forget what it's called, to the Omega solution, that sounds like a bad horror movie from the 1950s, but it's a product put out by Ohio Willowwood, to Rodin 4D. So there's a range of specifically produced digital CAD solutions for prosthetics. And then in terms of fabrication, again, and this is an image taken straight from Vorum's website of a series of options that they provide from various types of subtractive manufacturing technologies, milling solutions from 3-axis to multiple axis carvers of various types. Now, when I look at this, and then now the new stuff basically is the addition of additive manufacturing. So if subtractive is about taking material away from a blank to create a solid object with a complex topology, additive manufacturing is about building up objects with complex topologies from scratch using printers of various types. And there's a whole range of printers. And I don't want to get into the weeds here talking about those different printers, but just to give you a sense, the EOS selective laser sintering printers on the bottom start at about $1 million and go up. The printer on the upper right-hand side is a 3D system. No, sorry, 3D Systems Connects, which goes from about $250,000 to $500,000, and then the printer on the top there, the TAS, if you can read that, costs $2,500. Now, there is a difference here that you might start to notice between some of these printers and other ones of these printers and some of these scanners and other ones of these scanners, which is there's a dramatic reduction in cost and the development of a range of commodity technologies that can be and are being repurposed to be used within P&O professions. And then, of course, these are examples of some devices that have been produced using, in particular, additive manufacturing techniques. And I'll come back to some of the devices that my project has also produced later. So where are we? I don't want to get caught up too much in trying to place ourselves, but it's obvious that there's been sustained development from the 1980s to today. There's been developments in terms of shape capture, design tools, fabrication. There's also, and probably fairly recently, dramatic reductions in costs as more commodity systems begin being developed and utilized and customized for the P&O profession. Originally in my slide, it said evolutionary and revolutionary changes. There's a question mark because I'm still not exactly sure if they're revolutionary changes here or if they're all evolutionary, but I'll just take it for granted that they're both going on. But this all raises for me the question, and maybe it's not so much a question for you, but it was for me looking at this all from the outside. Why the slow adoption? Why have these technologies, which really date back for over 30 years, not been, kind of moved into the profession? And originally, I used to think that these were primarily around technical limitations, that these were problems that the technologies were not adequate for solving the problems in P&O. But I'm increasingly sure that that's not precisely where the problem lies. And I want to go back to this beautiful image done by Hugo Gernsback, who's a science fiction writer and an editor of a number of magazines back in the 1920s and 30s, to kind of talk a little bit about what's the missing piece in all of this, in this emerging technology and the P&O profession. So this is a quote, it was actually, sorry, not Radio Electronics, but from Science and Invention magazine from the February issue of 1925. And Hugo writes, "Here we see the doctor of the future at work feeling the distant patient's arm. Every move that the doctor makes with the controls is duplicated by radio at a distance. Whenever the patient's teledactyl," by the way, I want to patent that or copyright that term, "meets with resistance, the doctor's distance controls meet with the same resistance." So this is 1925. And in fact, if you go on through that article, the person actually notes that all of the technologies necessary to produce this device were in fact available in 1925. There was television transmitters and control at a distance and facsimile machines that could control all sorts of different mechanical linkages. All of that stuff existed at the time period. So why is it that it's not until it's about mid-2000s, 2005 or so, do we begin to see teleoperated medical devices like the Da Vinci robot that you see up there on the screen? So what is it that means that something that somebody posited in 1925 really doesn't come about for almost 100 years later? What was missing? This is what's missing. Successful technologies fit the social context of their use. In other words, it's not just about functionality. It's actually about how well the technology fits into the uses and organizations of the clinical practitioners, in this case, where they need to be located. It's not about functionality, it's about fit. And that's the claim that I want to make here today. And I want to give you some more concrete examples of that, and then end my presentation here today with some questions that I have for you around this fit and around the profession. So what do I mean when I say social context? Well, I'm using it in a very kind of simplistic sense to mean these things. Technologies move into context when they solve real problems, not things about feasibility, but actual usefulness. And one of the things that, if you go back to this, was that back in the 1925, that teledactyl device was feasible, but didn't solve any real problems. And the idea of the Da Vinci robot here is that it exists now because somehow it solves some real problem within the clinical context in which it's being addressed. The other thing that is actually less understood, but is equally important, is technologies are adopted when they facilitate the divisions of labor within the profession. In other words, the ways in which labor is organized, work and work practices are organized within a profession, if the technology troubles that, it's going to be very difficult for practitioners to adopt it. Oftentimes, that division of labor is marked by things like professional designations. So something like a prosthetic technician versus a prosthetist is a marker of the ways in which clinical activities are organized. And if the technologies don't fit that, there's going to be an issue. And finally, a technology gets adopted when it supports central ideas about expertise that are held by the practitioners. And I've seen this quite a bit within P&O. In fact, I wrote a paper on the idea of craft practice in P&O and how practitioners felt about the work that they did and the kind of expertise. There was a linkage in that paper between hands-on engagements with material systems and patients and the kind of expertise that prosthetists consider part of their profession. And so a technology that wants to be adopted within that area somehow needs to engage with that notion of expertise, as in any case where a technology is being adopted. So let me give you an example of how I navigated these aspects of social context in the development of what we called 3D printability, which was a prosthetic and orthotic tool chain for use in the developing world. And I'm gonna go through this part kind of quickly. If you want to know more about this project, I'm going to talk about it tomorrow, Thursday at I think at 12, and I'm happy to answer questions about it or talk to you outside of this context. So I'll go kind of quick. This project started about 3.5 years ago. The aim of it was to address this problem where there aren't enough prosthetic technicians in the developing world, and there isn't time to train them. So there's what we might call a wicked problem here. Can't train them fast enough to meet the need, and the need isn't currently being met. The idea behind our project was to take an existing system that's in place, the ICRC transtibial prosthesis manufacturing guidelines, and see how we could actually add functionality to that existing system, not replace it, but just basically speed it up. And the goal there, our idea there, was to basically get rid of the plaster room, which is a logic I've seen within Vorum and within a range of other CAD/CAM contexts. What did we do? Well, we took very cheap stuff. Initially, we took a Microsoft Kinect from a Microsoft Xbox, if people are familiar with that, to do the scanning. We used freely available software called Autodesk Mesh Mixer, and then some custom pieces we wrote ourselves to manipulate, design, and the digital scan data and to produce a socket model. And we printed them, those resulting sockets, on cheap printers, commodity printers, some of which you've seen pictures of before. So it was a 3D Systems scanner for about $300. Now, I should say now, originally we didn't do this, but now we've made an agreement with Vorum, who very nicely has provided access to their much more comprehensive design suite, CanFit software, so we use that. We do model preparation. The models that come out of CanFit need some work to actually produce definitive devices, so we wrote a software program called Orthogen that does that part of the process, both for sockets and now for AFOs. And we print them on a Lulzbot TAS5 FDM printers. We print them on 2, top and bottom, in order to get the print times down to about 1.5 to 3 hours. They're heat welded together, and those printers cost about $2,500 each. And then they're integrated with standardized ICRC components made of polypropylene. Here's a couple of examples. I don't think you can quite see them on the screen, but Jen and Moses are CAT2s, orthopedic technologists trained in Tanzania by CBBRT, I think that's right. At Korsu Hospital in Uganda, Ruth is a transtibial patient getting fitted. That's from June of this year. And then Samson wears an AFO because of post-injection paralysis, and he was fitted also at the same time period. That's a picture of those. I can show you these devices in person another time if you're interested. Our first trial, 35 PTBs, PTB-TT sockets and devices fitted. That's from basically up until August of 2015. Second trial just kicked off in June. 30 TT, 30 AFOs. They're about 13 AFOs in, 8 TTs in at this point. And we have a third trial starting in Cambodia. Okay, so that's a bit of the case. Let's go back to those social factors. Solving real problems, moving from feasibility to usefulness, divisions of labor, expertise, and technology. Well, one thing when we first started this work was we looked at a range of people who were doing work on prosthetics and 3D printing, and the first thing we realized was a $250,000 printer wasn't just going to fly, not going to fly in the developing world, it probably wasn't going to fly in the developed world either. So I don't know how many clinicians here feel like they could drop $250,000 on a 3D printer, but obviously that wasn't going to work. Plus, the material costs associated with 3D printing at that time meant that a device like these very odd-looking devices here would cost between $600 to $1,000 each, just in the cost of the material. So we decided to go with these low-cost stuff. So we wanted to make a usable system. We weren't just interested in feasibility. Material costs $3, $4, hardware costs $2,500. More importantly was this question of divisions of labor. We looked at and studied the social organization of labor in the Corsu clinic. We focused explicitly on Corsu. We interviewed and spoke with prosthetists and orthotists across the GTA, in Toronto. And we decided to organize it based on these CAT levels of technicians, technologists, and prosthetists. CAT 1 prosthetists do the scanning, very important, and do the rectification in Vorum's CanFit. They pass that on to CAT 2s, who open the resulting files in Orthogen and go through a much more menu-driven system to generate a device. And then that device is printed by CAT 3s, who basically run the printers. So we set the way the process worked based on the organization of the clinic. I mean, it probably doesn't sound very strange to use. Go, oh well, of course that kind of makes sense. But it's interesting because when we first proposed this project, what everybody wanted us to do was to have the clinical folks at Corsu Hospital in Uganda do the scanning, and then send the files over to Canada, where we have CAD experts and prosthetists who would do the rectifications and then send the files back to the clinical setting in Uganda where they would be printed. And actually, from a technical functionality point of view, that made a lot of sense. But from a social organization of labor point of view, it's really deeply problematic. I mean, not just because it breaks some of the organization of labor in those clinical settings, but also because it reifies existing power hierarchies between the global north and global south. I'll tell you, actually, something I don't think I say often in conferences, but I say often to other people, is when I talk to engineers about this and why we made this choice, they don't get it. They're like, well, why is that a problem? Distributed labor makes perfect sense. Take advantage of digital technology. And then I say, well, would you build a system that has the black people do the manual labor and the white people do the intellectual labor? Because that's actually what you're proposing to do. So these issues about social organization and the design of these technologies need to take these broader social contexts into consideration. And I think that's an important aspect of design work in this space. And then finally, there's this question about expertise. So Enable Foundation was brought up by Sylvia earlier today, and many people, how many people here were at ISPO in Toronto? Okay, so a lot of you have already heard some of the stuff I've had to say, but you also heard John Shull from Enable speak and the response from the P&O profession to some of these ideas. But the point here is to say that just because a technology is possible, just because it's feasible, doesn't mean that it matches the professional needs of a community who are, in fact, trying to innovate. And one of the things we've seen, and Sylvia pointed out, is the stories being told about these technologies often delimit the capacity and expertise of prosthetists, and that is another problem. But more importantly than the stories doing that is that we're now starting to see technological solutions in this space that build into the technology some of these problematic aspects of expertise. So what we are starting to see are more menu-driven systems where rectification isn't done by the prosthetist, and these are concerns. But these are not essential aspects of the technology. These are things that are being designed from people outside the profession, and they will have important effects on it. So these aren't problems with the technology. These are problems with the people making the choices and decisions about the technology. And so the question that I want to bring up with you all here today and highlight is not to talk about emerging technologies in the future of the profession, but to make the claim that the technologies are essentially here. And the question is, how do we fit them to the social and organizational context of P&O? And who, and this is really the important part of that, who should be doing that fitting? Three particular questions that I want to raise with you, and I'm not going to answer them, I'm just going to leave them with you here, and maybe we can have some conversation about it. are you comfortable with distributed rectification and fabrication? In other words, are you comfortable with having somebody else do rectification for you? Somebody else doing fabrication for you? If you're using digital fabrication, 3D printing and things like that, when and where do you think it's appropriate to pass off between the prosthetist or orthotist and the technician? Do you want the software to make that choice for you, or do you want to make that choice? Are you comfortable with centralized or localized fabrication? And how comfortable are you with patients having a more active voice in the processes of design? Because remember, once we have 3D models, we have the capacity to share 3D models. And do you want patients to have some capability of commenting or participating in their own clinical prosthetic process? And if you do want that, how should that occur, and what weight and capability should they have? And I want to end with this very troubling, I think, quote. And this is from a book called The Fourth Industrial Revolution. It just came out. Schwab is basically the director of Davos Economic Forum. So he's not an unpowerful person. He's somebody who has a lot of power. And he writes this. He says, many different categories of work, particularly those that involve mechanically repetitive and precise manual labor, have already been automated. Many others will follow as the computing power continues to grow exponentially. Sooner than most anticipate, the work of professionals as different as lawyers, financial analysts, doctors, journalists, accountants, etc., will be partially or completely automated. This is the world we live in, where computational technologies, deep learning, fabrication, 3D, all this kind of stuff is offering a potential future. Part of that has to do with automation. Part of that has to do with new capacities. And my only kind of feeling on this is that the group that should be making the choices about how this goes down is the group that's present here in this room, not people who are external to the profession. And so I want to kind of prompt you to take an active role in these developments. Thank you. Should I do the, okay, so what I'm going to welcome some voices from within the profession, as opposed to people like me from outside of it, to come join us on the stage and take part in this panel discussion. Those people whose names I have here are obviously Geza, and who you've already met, Bram Koch, Michelle Weimer, and Dan Mazur are all coming. And you know, guys, I don't actually have your bios in front of me, but based on what I've heard, is everybody kind of knows everybody here. Is that basically right? Okay, so I'll go ahead and let them do. Should I, and I think I've been kind of tasked with shepherding this process. It was so well done this morning, I'm a little embarrassed. I hope I'm able to do it well enough. But my goal here is to basically just move the questions to the experts over here and help everybody move forward. And I think I also need to move the screen to this question forum and invite you to either come to the mic to ask questions or also to put them into this. Oh, is that right? All right. And I don't know, and maybe just to kick us off, I might invite the panelists here to say a few words. Does that sound like a good idea? So maybe we'll start with you, Michelle.
Oh, me?
Yeah, absolutely.
I love talking. My name is Michelle Weimer, and I manage our North American accounts at Vorum. So we've kind of heard Vorum a little bit today, and I guess my thoughts with respect to technology, and for those of you who were in the break earlier, I think the industry is moving towards technology. I think it's here, as Geza and Matt were saying, and I think that Matt's last question is, who do you want to lead the charge? Do you want other people to make decisions for you, or do you want to be the ones making the decisions with the direction of the field? And I think that statement is precisely where you're at. There are more pressures today than ever before. How do you do things differently? How do you move forward in the field? And if you don't move forward, you will end up getting left behind. So those are kind of my thoughts on this whole piece.
So we just go straight down the row there, yeah.
Okay, so I'm Dan Mazur. I'm the Director of Pino at the Root Center for Children in Winnipeg. I'm a CPO myself, and we just jumped into this whole CAD-CAM thing with both feet. We've got the carver and the scanning apparatus. I think I've also done a little bit of sort of experimental work with a 3D printing firm in the city in Winnipeg, and just looking at how it all came up was I was approached by an engineering technologist wanting to know how to create some of these open source devices, and looking at if there's value and how do we find the value into that. So we just kind of let it snowball from there. So it was a really good learning experience, and I think that we really do need to be involved in this process. What I learned as the process orthotist, we really have a lot of subject matter knowledge that we can use to drive this and use the technology properly. So I'm excited to see where the future goes, but some of my questions that I'll touch on in my presentation later in the week is that whole concept you really hit on, is the reorganization of work. Our new practitioners that are coming in, are they equipped properly? And then really looking at the technician's role as well, and how that will fit with operating the new technologies, or do we need to be recruiting different types other than just the GBC track or the on-the-job track? Maybe we need to be recruiting other types of technicians into our industry as well.
My name is Brian Coke. I'm a certified prosthetist in Winnipeg in a private clinic, and I think everybody's hit on it. That's been the kind of the underlying theme here for sure, is that technology's changing. I think as much as we like to hold back and things, I think there's really the only option is to adapt. And as Sylvia had said, who's going to tell that story? And I think that's something that's going to resonate with me for quite some time, is that it's definitely, we want it to be us. We look at the media, they're pushing things in that way. As far as the technology, we have a CAD-CAM system, and we do struggle with it and things, but I think in the early adopting phase, we certainly will. I think it's how we rise to that challenge and come to that. And I've sort of had to internally look at what are the best ways that we implement this. And I think that's where some of the challenges will lay. You can't just push it to the side and hope for the best, because we will definitely be left behind. So I think it's really exciting times for sure. How we rise to the occasion, I think, is really what comes to it.
So we're getting all sorts of questions up on the screen. I don't know if others want to take a thing, but I actually wanted to comment on the very first one. If not us, who will provide prosthetic services in the future? Well, if you listen to John Shull's speech at ISPO back, I guess a couple of years ago now, over a year ago, it was hobbyists. It was just, you go onto a computer system and download a model and print it, and then you're done. So that was the story about who is going to provide prosthetics in the future. Now, obviously, that's not a very functional story or a very good story, but I think there are movements towards that direction, towards prosthetists in a box kind of ideas, where you don't need certification or training in order to provide these devices. And I mean, I want to be clear here. I'm sure you guys aren't. I don't think anybody who knows anything about the profession would want that. But that is one of the pieces of the story that's being currently told. Does anybody else want to comment on that question? We're just running. There's so many of them up there.
I'll make a comment on the first one, but more general, both orthotics and prosthetics. I'm looking at students that, as I mentioned, are coming in with other disciplines that want to be involved in orthotics and prosthetics. And that drive that they have, I've never seen such motivation from students, and I've been involved in academics teaching 30 years ago, but they didn't come with that kind of drive. And so if we don't embrace the technologies that they want to engage with, they will break off and they will do it better than we ever could even conceive. So I think that ideas like some of the ones I brought up, like powered orthoses, we need to bring those people in, embrace them, to engage with us, to show how these new ideas can advance our field. And so I think it will get away from us, because those skill sets are different than ours as clinicians, and that they need to mesh. So we need to embrace them.
Should we move to a different question, or do you guys want to take a stab at that first one? Because I think this one about cost is kind of, oh, I'm sorry,
Yeah,
Brian.
no, I was just
Brian.
gonna say, like, when we're looking at the fabrication and who's gonna be doing that and providing services, I think one is the actual fabrication component, and that's very, if anybody with a printer can do that. But I think we all know as prosthetists, orthotists, we provide care. So that care aspect is never gonna be lost, and I'll steal from Michelle's presentation, it's all CAD/CAM and all these things are different tools in the tool chest that we're using. So I think still the orthotist process is relevant. Maybe we won't do the fabrication. I guess that remains to be seen. But I think it's really just we have to reinvent ourselves in a way. But still, the care that we provide, we are the providers, I believe, of choice there for sure. So.
And the clinical expert. So you don't want it to be anyone else. Like, it shouldn't be anyone else. You should be leading the way, right? I think that's a fair statement.
Does anybody have a comment on this question? The major barrier to incorporating technology into practice is cost. Suggestions on how to bring technology to practice in a practical way. And I'm assuming in a cost-efficient or cost-effective manner for a particular practice. Is that?
I can comment on that. I think historically with CAD, people have thought about CAD/CAM as the whole solution. So expensive scanners, CAD software, and carving machines, so the CNC machines. And if you put that all together, it's a pretty big cost, especially for smaller clinics. There's certainly been a transition towards central fabrication. So now in Canada, you actually have central fabrication facilities that can offer either carving services and send you back the mold to so you can still control your fabrication, or fabrication services. So places like the Knee Center at Carl Hager or Myrdal. So you don't have to go all in, and the cost of scanners has come down significantly. So if you look at just those first two steps, which is getting really accurate data in that shape capture, and then leveraging the digital plaster room, that the price point has gone down significantly where people can invest without actually having to get a big machine. And there are different, models around that, but that has lowered the barrier to entry and then enabled people to start to see that return on investment they need to show that it's worth the investment. So, and I think actually, Bram, that's the model that you leverage, right?
Yeah, and it's one of those things that even if you run into issues, you have to kind of find creative solutions on how you're going to use this technology. Yes, there's the base that CAD/CAM gets showcased, but there's definitely other areas where you can streamline, and there's benefits that I for sure didn't immediately see, but it does work quite well in that way. So I think at the end of the day, yeah, the barrier to entry has come down quite a bit as far as cost goes, and I think if we just stick with plaster, I think that just the demands of patients are that we keep up with what's there, because it is in the media and it is where things are going, and I do believe that is where technology and what is best for patient care.
So I have a comment to expand the discussion of costs. So this discussion is about the cost for manufacture. What I was trying to propose is new paradigms where there's new tools that we will use on the treatment side of it. I think that those costs will be paid for. I use the cardiology model again. We all get EKGs. We all get monitors put on us to evaluate our heart rate at home if you're being treated for someone like that. And the reason why is because it was demonstrated that that was valuable to a treatment decision. So I think this is a way to expand the need for doing these tests so that when someone's going to be evaluated for an AFO, they'll have a test. It might be done by a technician that will put on this instrumented AFO, take a set of measurements, give it to the practitioner, and he'll make a decision based on those. And I think we'll get reimbursed for that. So we're talking about cost of manufacturing, but there's other things that we can now, I hope we would be able to bill for, and we'll be able to demonstrate we will from evidence that says that's necessary for treatment.
Yeah, and I just want to add one more point just to the manufacturing cost, especially with reference to this, 3D printing, because the biggest, I think, problem with the devices that end up in the media is they're all produced on really low quality printers with low quality materials, we're looking into those printers where we're up in the $250,000 or $1 million. The way that I looked at doing my case study was just seeing what kind of collaborators were available in the city or relatively close by that we could just look at having them do the central fab work and how the materials that we could get out of those higher quality printers would compare to what we're typically using from injection molds, and being able to customize that better, because even if we can create a similar device that's cost neutral but is more customized in terms of the cosmesis and the durability and the size of the components, which is something I always struggle with in a pediatric facility, that would be good, because there's nothing really wrong with the way that the treatment we're providing now, just looking at doing it in a different way to provide more options. So I think what I found is that using someone locally who had a really good printer that was paid for out of research money from the province, we could acquire the components that we needed for a fairly reasonable cost.
There's a great question here about, are there unbiased studies on the clinical effectiveness of the devices made by CAD-CAM technology? And I guess I might say, CAD-CAM here, CAD-CAM, by the way, stands for computer-aided design, computer-aided manufacturing. That covers a gamut of sins, so to speak. But in the prosthetics, what I've seen is that most people use it to refer to the kind of standard design tool chain, followed up by subtractive forms of milling. And I have to imagine that there's, I've seen a lot of literature. I don't know how unbiased it is, so I'll let the...
Yeah, and well, to me, I haven't seen a lot of studies that compare it that are published. I think right now there are people that are publishing comparing traditional techniques to 3D printing, which, they're missing the piece on the CAD-CAM, which is more efficient. I would love to see some. Vorum can't fund any because then it wouldn't be unbiased. It wouldn't be viewed as unbiased. But what we do have is we have data from our customers. So for us specifically, when we're providing data around improved efficiency and the effectiveness and the outcomes that our customers are seeing, it's based on the data that they're providing us. And I think Dan can probably provide some examples, but we're setting benchmarks in the beginning, comparing plaster. We're setting we're setting goals along the way to assess the effectiveness of it from an efficiency perspective. It's still anecdotal with respect to fit, and it's still based on the clinician's expertise and experience and their sense with their patient interaction. I haven't seen any quantitative studies showing it per se, but I can say based on the 700 plus installations we've done, that it shortens the turnaround time. It's more efficient. I can say that, but I can't point you to any studies. So specifically.
Yeah, just to add to that, I think the problem with the lack of studies in this realm is the issues that we're seeing all over in our industry without having the time or the expertise or the resources to put these types of studies together. But for our practice, when we looked at really jumping into this, we had kind of acknowledged that we're going to have to really relearn how to do some of this work, and the software is not magic. It doesn't think for us. It doesn't replace the clinical skill set that we have. So in our realm, we're kind of looking at our clients were happy from the quality metrics that our facility used, so we want to be able to keep them just as happy or happier in a shorter amount of time.
Yeah, I don't know how unbiased it is, but we didn't do a comparative study with our first clinical trial in Uganda, but the ones that we're doing currently, we have 30 transtibial, 30 AFOs. Each of them is being fit with a 3D printed, digital process 3D printed for 4 weeks, then being fitted with a standard polypropylene one for 4 weeks. And then we're doing we're doing a series of quantitative measures associated with each of those. It's not a very long-term study. It's as long as we can do it. But hopefully by this time next year, we'll have some data about that. But the problem with it is the dependencies are so much about the skill set of the prosthetist. The skill set of the prosthetist is this much of the quality of the device. The manufacturing technique is this much of the quality of the device. Anecdotally, that's what I can say about what I've
Yeah.
seen so far. And so variation you see in patient outcomes is typically dependent upon the capacity of the prosthetist, not on the manufacturing technique that you've utilized. But I think you have a question.
Yes, I have a little comment here. So we develop rapid manufactured orthosis and prosthesis and also spin-off companies. And I would, if one of you would look into this field, I would recommend not to invest into a machine directly. And I'm fully with you. I would even say the development of the new materials, the resins, the machines is that fast and surprising, even if you're in this, that ideally you take the 2 or 3 best Canadian prototyping contract manufacturers. They can ship you the components you require within the same day. They use the latest machine they have and will make the component that you designed. There are more and more elastomers, which were not there in the past, and technology is changing that fast. Hewlett-Packard now has, only for 2 months, this super fast printer, much faster than any other there was before. And I would always keep this to other people who have to live on the machine, who may even only license these machines, so you get the best part and don't get stuck in an invested machine and try to make the best out of it. The change on the machine is so fast that I think that's too early to buy one.
Well,
I would make, if I can make one caveat to that is, so in my experience, so we did a lot on FDM printing, the plastic-based printing, with inexpensive printers. And one of the things that we found is controlling the printer, controlling the process of toolpath generation, controlling the temperature at what it's printed, and optimizing all of those specifically for the production of devices, prosthetic and orthotic devices, is actually key to the success. And so one of the problems with using a general service bureau is they're not going to know how to optimize their printing processes necessarily at this point for P&O devices. And so you have to be a little bit careful, because it turns out that level of stuff, that really deep technical level of how things are printed, has really quite strong clinical, can have quite strong clinical outcomes, which is why in my project we actually control all of it from beginning to end, simply because we can't trust that we're going to get the results that we want otherwise. I think there's a lot of other questions, and I guess we'll just take them in order. Does anybody want to try to address this top question? Can you guys read it? It says, when do you think clinicians should control all aspects of shape modification, and when should we pass some responsibility on to technicians or centralized fabrication? That's quite a nice question.
as clinicians.
That's a pretty open-ended question, but from my standpoint, I think that's where clinical decision comes in. I can see there's times where as a clinician, I want to control the entire process, and I think that's, again, coming back to our skill sets as during the assessment and all the stuff that makes us clinicians. I think that's where we decide that, if I'm reading the question right. That's the way I would see that. There's times when I use CFAB, and there's times when I keep it all in-house, and there's pros and cons to it depending on the materials you want to use. If you wanted to use a 3D printing, we don't have 3D printers in-house, so that's where it makes sense maybe to go to CFAB, or carving, send it over to CFAB for carving. It all depends what the end result is, and we know that all our patients are unique, so what would be the best result there? So,
and I'm pretty similar in that regard. I think a lot of it is driven by the assessment, the complexity of the client, the pathology, the limb, the tissue. If it's something that I think using my assessment, having my hands on the patient, I need that information to complete the modifications, then it needs to be done by myself. But on the less complex ones, or certain parts of the process, if it's just cleaning up the scans or having people scanning casts that we've already taken by hand, then that type of work can be passed on to different personnel.
I wonder, Geza, if there's something about when you were describing your education program. One of the things that struck me was that the students that come out of that program would probably have some capacity to evaluate technological systems that they're being presented with, which is something I think that's essential to making the kinds of choices that we're talking about here today. What do you have any comment on?
Well, let me give you an example of what our graduates, how creative they are. So we had two graduates. One was a biomedical engineer. another one a physics major. These two buddied up. They did their residencies, then they started practicing, went to different areas of the country to practice. They needed a printer, so what do? They did one of these online funding crowdsourcing.
To get a printer.
And I mean, this is just that's who we're dealing with right now. And that is really making a difference. They're just very creative to get what they want.
Well, the other part of that would be, I think being able to evaluate the solution space that you have available to you and make good clinical choices on it, that seems to me to be an essential skill set for many professions, many clinical professions these days. Knowing what the limitations are of a particular way of doing something and being able to make decisions that result in the kind of outcomes you want for your patients. Knowing when to do the whole thing, knowing when to pass it off, it seems to be part of what it means to be a frontline clinical person. We only have 2 minutes left, and we have about 5 more questions that haven't been addressed yet. I wonder if any of the panel wants to choose one of those, feels compelled to speak about one in particular. So many. I mean, I think this question about embracing technology just because it's the new way, I obviously, maybe not obviously, but I think that's, I think anybody here in the room that doesn't feel like these technologies are going to offer a benefit to their practice, they really shouldn't engage with them just because they're new. For the clinical context that I've been engaged in, there's a need. And the 3D printing technology, the digital process, serves a need. It basically changes the turnaround time from a week to 1 day. So it is about efficiency, to speak about one of the other questions there, but it's also about creating outcomes that are good for the patients that are involved, but it's also about serving unmet need. So that's why, if it wasn't for that, they wouldn't be interested.
Yeah. And I think with respect to CAD-CAM, it's not new. I mean, this has been around for 30 years and evolved significantly over 30 years. So to say that it doesn't have the clinical benefits, I think we are not really looking at the, I think we're just pretending if we don't think that there are clinical benefits to embracing technology. It's not new, it's there. I mean, there are other pieces of that technology that are new around 3D printing, and things are moving certainly in that direction, but we just can't keep pretending that the industry isn't moving forward and isn't evolving. It happens in many industries, so.
All right, I see the first word up there was finished. This session has finished. Right now we're going to take a break. I'd just like to thank Geza, Matt, the distinguished panel for, again, creating some very good conversation.